the circle angle theorems. So before going into the theorems, we have to look at a few important terms that are involved in these theorems. The first one is an inscribed angle. What is an inscribed angle? An inscribed angle is an angle whose vertex lies on the circle and whose sides are chords of the circle. Right? So an inscribed angle is that whose vertex is on the circle. So this is a vertex. Let me show you the parts of an angle. We have here an angle. So this angle is made up of two rays. Those two rays having a common endpoint. Right? And that common endpoint, we call it as vertex. This is the vertex, and this is the angle. It's measured in this way, and you have a side here. That is the side 1. Usually we call it as the initial side, the starting one, and the other one is the terminal side, the end side. So those are the two sides of an angle, and the common end point is called as the vertex. Now, so in this circle, those two blue lines are the chords. We already defined what are the chords, right? The segments having the two endpoints on the circle, those are the chords. This is chord 1, this is the other chord, right? And those two chords have a common endpoint. Hence, this particular angle, this angle is known as an inscribed angle. So it is satisfying all the conditions, right? An angle whose vertex lies on the circle and whose sides are the chords of the circle. So those two are the chords. Alright, so you have an inscribed angle. Now similarly, we have another angle over here that is called as central angle. This angle is the central angle because the vertex is at the center. This is the center of the circle. Let us say P is the center of the circle, and those two are the radii. Hence, we call it as a central angle. Central angle is an angle whose vertex is at the center of the circle. Alright, so this is the central angle. And intercepted arc. An intercepted arc, when two straight lines cross a circle, the part of the circle between the intersection points is called the intercepted arc. And the intercepted arc might be thought of as a part of a circle which is inside the inscribed angle. So here we have inscribed angle, this one. This is our inscribed angle, right? From this is one side and this is the other side, and the inscribed angle, and you are talking about those two straight lines. And here I have taken a ray for our understanding, and this particular part, this region or that arc of the circle which is inside this inscribed angle is called as an intercepted arc. Here this is the intercepted arc. Now let me show you by taking some symbols like letters. I'll call this point as A. Let us say this is A here. You have B, and over here let me call that point as a C. It is C I have. Okay, C is the vertex. A and B are the two other endpoints of the chords. So this angle ACB, that angle ACB is the inscribed angle. Angle ACB is the inscribed angle. And the central angle is angle APB. Angle APB and the intercepted arc is this arc AB. Okay, and in this study we generally measure this intercepted arc in terms of angles. We know that the whole circle makes 360 degrees. So the measure of the intercepted arc will be always less than 360 degrees, and in this case it is less than 180 because it is a minor arc. And also we are going to understand that the central angle is always equal to the intercepted arc. That is, the measure of this angle APB, the measure of angle APB is always equal to the measure of the arc AB, this arc AB. And in the next slide we are going to look at the relationship between the inscribed angle and intercepted arc. So right now please remember that intercepted arc is same as the central angle. Their measures are equal. Now we have a theorem. Its a statement goes like this: the measure of the inscribed angle is half of the measure of the intercepted arc. Okay, the measure of the inscribed angle, means this angle, is always half of the measure of the intercepted arc, this arc. Okay, so you already know about these three terms, right? What is the inscribed angle? It is over there, that is the inscribed angle. This is the intercepted arc, this piece of the circle, and central angle, we know that it's at the center. Okay, now the relationship between the intercepted arc and the inscribed angle is that the measure of this inscribed angle is always half of the measure. That is, for example, if the measure of this intercepted arc is 80 degrees, this arc is measured 80 degrees. So what is half of 80? Half of this 80 is equal to 40 degrees. So the inscribed angle's measure is going to be 40 degrees. Now let us prove this relationship between intercepted arc and inscribed angle. Just now we observed that through the statement of the theorem, inscribed angle is half of the measure of the intercepted arc. Okay, now these are the three different cases that we see with reference to intercepted arc and inscribed angle. In the first case, here we are seeing that intercepted arc AB we have there, and the inscribed angle, this inscribed angle is over here. This is the inscribed angle, and the center of the circle is on one of the sides of this inscribed angle. P is on this AC. Now in the second case, we are seeing that this is the intercepted arc, AB is the intercepted arc, and the inscribed angle you have there, over there ACB is the inscribed angle, and the center of the circle is lying inside. It is in the interior of the inscribed angle. And in the third case, we have inscribed angle over here, that is ACB, and the center of the circle is outside this angle ACB. Whatever may be the case, we have to prove that the measure of angle ACB, the measure of the inscribed angle ACB, should always be equal to half of the measure of the arc AB. So the measure of inscribed angle ACB is equal to half the measure of AB. That is, inscribed angles are always half of their intercepted arcs. Now let us look at these cases individually. In case 1, we are seeing that the center of the circle lies on one side of the inscribed angle. So, and we have to prove that this measure of angle ACB, the measure of angle ACB is equal to half of the measure of the arc AB. Alright. So how do we prove that? Now, in order to go to the proof of this theorem in case 1, we need to know about the properties of a triangle. We know that in any triangle, the measure of an exterior angle is equal to the sum of the remote interior angles. What does it mean? That is, suppose if the measure of this angle is, let me take 40 degrees, and the measure of the second angle is, let me take 30 degrees. And now what is the measure of this third angle? That must be like, this is 40 plus 30, 40 degrees plus 30 degrees, adding you got 70. And we know that in any triangle, sum of the three angles is equal to 180 degrees. So from 180, if I take away 70, you have 110 degrees. So this measure is 110 degrees. Now, the statement states that the measure of exterior angle is equal to the sum of its two remote interior angles. Okay. Now, let me extend this side. Let me just extend one of its sides. So now you have an exterior angle, right? This is the exterior angle we have. Now, what is the measure of this exterior angle? By making use of our knowledge of a straight line. You know this is a straight line. In this straight line, anywhere on the straight line, the measure of the angle is 180 degrees. This whole thing, this total has to be 180 degrees. The straight angle, this measure is how much? 180. Now out of 180, 110 is gone there. Out of 180, we already used 110 here. So from 180, take away 110. What is left? That is 70 degrees. So the measure of this exterior angle, I'll remove it here, and the measure of that exterior angle is equal to 70 degrees. Now you see, this exterior angle is equal to 70. Now for this exterior angle, what are the remote interior angles? Leaving this in this triangle, leaving that 110, the other two are the remote angles. That is 40 plus 30. 40 plus 30 is 70. That 70 is same as the 70 here. Even if you extend this side, now this will be the exterior angle. This is the exterior. Its measure is again 30 plus 40, that is 70 degrees. Similarly, one more quick example let me take. Now this is the exterior angle in this triangle. Now the measure of this exterior angle is equal to sum of those two. Suppose this is like 60 degrees over here, and let me take this is 50. Well, now what is 60 plus 50? That is 110 degrees. The exterior angle is equal to sum of the two remote interior angles, right? That is one thing I have to know in order to prove our theorem there. Now the second thing, in an isosceles triangle, the angles opposite to the congruent sides are congruent. What is an isosceles triangle? Isosceles triangle is that in which two sides are congruent. So here in this triangle, we can see that those two sides are congruent. Let me call it as triangle ABC. In this AB, the side AB is congruent to the side AC. Now, what are the angles opposite to AB and AC? For AB, the one opposite is the remaining vertex, that is a C. C is the angle opposite to AB. Now, what is the angle opposite to AC? This is AC, opposite is a B, the leftover vertex, that is angle B. And those two are congruent. So the angles opposite to congruent sides are congruent, and other way, even the sides opposite to congruent angles are congruent. So in an isosceles triangle, you'll have two sides equal to each other and two angles that are equal. Having this information about the exterior angle and about the isosceles triangle, I can easily prove our theorem. Now let us go back to the case 1. Here we have what ACB is the inscribed angle and AB is the arc. Now let us consider triangle BPC or BCP, whatever you call. In this triangle B, C and P, we are seeing that PC is congruent to PB, right? The side PC is congruent to PB. Why? Because those two are the radii. P is the center, PC is one radius, and again P is the center and B is a point on the circle, PB is the radius. So because those two are the radii, plural form of radius is radii, those two sides are congruent. Hence, the angle PCB, this angle PCB is congruent to the other angle PBC. Angle PBC. Right, so opposite to PC you have PBC and opposite to PB you have PCB. So those are the two congruent angles you got, right? Using that isosceles triangle. Triangle BCB is isosceles because the two radii we have, right? And then let me use this exterior angle. So in this triangle BCP, angle APB is exterior angle. Exterior angle APB is equal to, what are the two remote angles for this exterior angle? You have C here and this is B. Its full name is those two, PCB and PBC. Okay, I will add those two interior remote angles in order to get the exterior angle APB. So the first one is angle PCB plus the second angle PBC. Okay, now that is same as angle PCB plus angle PCB again. What I did here is I brought the PCB the same thing, but instead of writing angle PBC, I changed it to PCB because PBC is same as PCB from this property of isosceles triangle. Instead of angle PBC, I can write PCB, right? Now, what is angle PCB plus angle PCB? Is nothing but 2 times angle PCB. See, everywhere we are considering its measure, the measure of angle PCB in fact. Now, this exterior angle APB, is equal to 2 times PCB. Now, if you divide by 2 on both sides. If you divide and divide this by 2, you got 1/2 of the measure of angle APB is equal to the measure of angle PCB. Okay, and this APB is nothing but your central angle, right? APB is the central angle you have, and PCB, this is PCB. Instead of calling it as angle PCB, you can also call it as angle ACB. See, whether it is PCB or ACB, it is just the same. Let me show you that thing. This is angle PCB, right? PCB, this way. And even ACB from this way, if you call, it is just the same angle. It is just the same. So whether you call it as angle ACB or PCB, it is just the same. So instead of writing PCB, what I'm going to write is ACB. So the measure of angle ACB is equal to half of the measure of angle APB. You know that APB is the central angle. Half of the central angle equal to the inscribed angle. This inscribed angle, so measure is half of that central angle. But APB, you already know that it is nothing but the intercepted arc. Whatever you have at the central angle, it is same as this arc AB. Hence, I can conclude that the measure of angle ACB is equal to half of the measure of this arc AB. Half the measure of the arc AB. That's what is required to be proved. Okay, this is one part. Now in second case, we have to prove once again the same thing has to be proved. What is that? The measure of angle ACB is equal to half of the measure of arc AB. So in order to prove that, we have to make use of case 1 to get the case 2. So let us just draw one ray, right? One ray, or you can even draw a segment. If you want, you can just stop it at this point. That's fine. Now I'll call this point as a D. Okay. The scenario, the given case is the center of the circle is inside this inscribed angle. So in such a case, we are connecting the vertex C with the center and it is extended. Now what happened is, we brought it into almost like the first case. In case 1, you said that we have proved that if the center of the circle is on this side, this angle ACB is half of that arc AB. This is what you got in the case 1. Now we are making use of that same thing. So in this, now we have 2 inscribed angles and 2 intercepted arcs. So we look at one thing at a time, at a time. Like, this is the one AC and this piece we are looking at. The other one is here. Okay, so angle, the measure of this angle ACD, the measure of angle ACD is equal to half of the measure of what arc? This arc AD, right? Because the center of the circle is on one side of this inscribed angle by making use of the case 1, which is already proved, that angle ACD is equal to half of this AD. Now similarly, take the other angle here, the second inscribed angle. This is the second inscribed angle. That's the first and this is the second one. With reference to this, what happens? The measure of this inscribed angle DCB, the measure of inscribed angle DCB is equal to half of the measure of this arc. I should have written M here, the measure of arc, what? DB. So from first angle you have obtained the measure of angle ACD is half of AD. Now from the second inscribed angle we have angle DCB equal to half of this measure of angle DB. Okay, so this is the second case. Now I'll add those two. Let us just add these two angles, measures. What do you get from that? Measure of angle ACD plus the measure of angle DCB is equal to half of the measure of angle AD plus half of the measure of angle DB. Okay, now let us add inside these two angles. What is ACD plus DCB? Angle ACD is this piece, right? And what is angle DCB? DCB is this second angle. Adding the first angle to the second angle, you'll get this whole big angle, right? And what is the name of this angle? It is ACB. So the measure of angle ACB, on adding these two small angles, you got that big angle, equal to half and half is the common factor. Take it out. And the measure of AD plus measure of DB. AD is this arc. This is arc AD. Plus next arc DB is that one. Adding the two arcs AD and DB will give us the whole big arc AB. So half of the measure of the arc AB. That's what is required here. The measure of angle ACB equal to half of the measure of this intercepted arc AB. Right? This is how the case 2 is proved, making use of the case 1. Now let us go to the third case. In this third case, the center of the circle is in the exterior of the inscribed angle. This is the inscribed angle, but the center of the circle is outside this inscribed angle. Okay, then what do? Just connect this vertex and the center of the circle, and you got one side here. And let me call this as a D again. This point where it is touching the circle, I'll call it as a D. And our requirement is the same thing. We have to show that this measure of angle ACB, the measure of angle ACB must be equal to half of the measure of this arc, that is the arc AB, with reference to that inscribed angle. So half of the measure of the arc AB. Okay, and already we have this construction. You have drawn one ray here that is passing through C and center of the circle P. Okay, now what happens here? Let me consider this big angle first, right? That is again an inscribed angle, and its name is DCB. So DCB is an inscribed angle with reference to this intercepted arc. What is the intercepted arc for this? Starting from D, all the way up to B, right? That is the intercepted arc. All right. Now, using your case 1, what is the value of this angle DCB? The measure of angle DCB is equal to, measure of this angle DCB is equal to half of the measure of this arc DB. Okay. Alright, this is DB you have here. This is DB. Now, this is, let me call it as the first angle. So, I got equation 1 here. Now, second angle, we will consider this as the second angle. See, we have to make sure that one of the sides of this inscribed angle has a center lying on it, like your case 1. If the center is one of those two sides, then that case 1 is applicable. That's why we are now taking this angle DCA. So, the measure of this angle DCA, the measure of angle DCA is equal to half of which arc? For this particular angle, my arc is this little arc DA. See, DA and DCB, they are connected. For this intercepted arc DA, my inscribed angle is DCA. That's why the measure of angle DCA is equal to half of the measure of arc DA, right? And this is from your second angle. I am calling it as second equation, and we will subtract in this case. In case 2 we added, here we will subtract equation 1 minus equation 2. That is, the measure of angle DCB minus the measure of angle DCA is equal to half of the measure of, I am even taking the common factor, half of the measure of the top one first, DB minus DA, the arc DA, the measure of the arc DA, of course. Okay, so what is here now? DCB. Where is your angle DCB? D, all the way up, DCB is this angle, this whole angle 1. From that DCB, we are taking away DCA. Okay, so let me use this here. This angle, this is the whole angle, right? From that angle DCB, we are taking away this little angle. Now, what is left over? Now you are left with this piece, right? The yellow one is the big angle DCB, and the next one, this blue one, is angle DCA, and the remaining, the purple, is the remaining one. Okay, now on subtraction, we have DCB minus DCA gives you this angle ACB. So the measure of angle ACB, that is subtracting this DCA, subtracting this little angle DCA from the big angle DCB, you are left with this angle, that is ACB. That is equal to half of the arc DB minus DA. See, the DB is this green line, this whole arc is DB, and DA is the blue one. Now, what is left over? From D to B, you took off up to this piece. This piece is gone. So, you are left with this piece. Starting from A, went all the way up to B. That is the half of the measure of this AB. The leftover thing, that is from DB, take away From DB, take away DA, you are left with AB. So now this is nothing but the required proof. The measure of the inscribed angle ACB is equal to half of the measure of that intercepted arc AB. So altogether, these are the three cases that are existing with reference to the relationship between the inscribed angle and intercepted arc. Okay. So now we know that inscribed angle is equal to half of the intercepted arc. That is, like I said, if this measure is, let me take 78 degrees, the measure of this intercepted arc is 78 degrees, the inscribed angle will be half of 78 degrees, that is 39, right? Similarly, we can solve any problems dealing with the inscribed angle and intercepted arc. So here you are looking for x. Find the value of x. If you want, you can pause it here and try to answer. Find the values of x and then verify. Okay. Let me show you now. This is x. The measure of that inscribed angle x is half of intercepted arc, that is 130 degrees. So half of 130 is 65. X is equal to 65 degrees. That is my first answer. But in this case, you already know the inscribed angle, that is 85 degrees. And that must be equal to half of your intercepted arc. This is the arc, right? So half of this arc. The measure of this arc, they are saying x degrees. So that x is here. Half of the x is 85. Now, what is x? There are so many ways you can do, either cross multiply or multiplying by 2 on both sides. On multiplication, 2 times 85 is how much? That is 170 degrees equal to half times or half x times 2 is just x, or half times 2 is 2 halves, that gives you 1, that is 1x. The value of x is 170. See, 170 and half of 170 is 85. Okay, that's good. Now, the third case here, it is a little bit different. How do you find the value of x? To find the value of this x, the inscribed angle, I need to know what is the intercepted arc. Do you have that intercepted arc here? No, I don't know. They didn't give us. But you have the information about the remaining arcs or the remaining parts of the circle. In fact, this whole circle is divided into 3 unequal parts. Now, this is 112. I have 112 degrees. And the second angle is 126 degrees. Now the third one we do not know. Add them. 112 plus 126, that is 8 here. 3, 238 degrees. Having known that the measure of the whole circle is a complete angle 360 degrees. From 360 degrees, if I remove out these two pieces, that is 238, take away. That gives me what here? That is 10 minus 8 is 2. 5 minus 3 is 2 again. Right? That is 122 degrees. 122 degrees is this inscribed intercepted arc. So 122 degrees. If the intercepted arc is 122 degrees, what is this inscribed angle now? Just divide 122 by 2. So half of 122 is 61 degrees. The value of x is 61 degrees. Now we also have some special cases, like an angle in a semicircle is a right angle. We can prove it by making use of the same relationship inscribed angle is equal to half of the intercepted arc. Now they're saying that it is a semicircle. This is the semicircle. The angle in a semicircle is a right angle, that is 90 degrees. This measure is equal to 90 degrees. How do you know? I know it because this is a diameter, right? Once you have a semicircle, means one of the sides is a diameter and has a center here, and this angle is a 180 degrees. Okay, if this angle is 180 degrees, you know that the measure of the semicircle from 360 is 180 half, and even the intercepted arc is also 180 degrees. Now half of this 180 is 90. 180 divided by 2 gives you 90 degrees. So an angle in a semicircle is always a right angle. It can be in this way or having the same diameter. If I have a triangle like this, let me use a regular line. This is a right angle here, that is 90 degrees, and even this angle is also 90 degrees you'll have. And we have one more case here. Angles in the same segment of a circle are congruent. That is, this angle, suppose if the measure of this angle is 50 degrees, even the other angle is also 50 degrees, because they have the same intercepted arc. Because this arc is the same, all those angles are going to be the same. So here, according to this example, that's 50, so this has to be 100 degrees. The measure of the intercepted arc is 100, so inscribed angle is 50 degrees, 50 degrees. Even if I take a third one here, this is also 50 degrees. This measure is 50, that is 50. Likewise, you can come up with any number of angles. All the measures will be the same. So that's all about your angles, the relationship between the inscribed angle and intercepted arc. So please try your own examples. Thank you. Thanks for watching.